All right, in chapter 4, we're going to switch gears here, and we're going to do integration, which is antiderivatives or working backwards. All right? Given a derivative, working backwards to the original function. All right? Given a rate of change, I can work backwards to the original. If I have a change in cost per year, I can get back to the cost function. All right, so first, antiderivatives, because they're part of integration. All right? Integration is the process like derivatives. Finding antiderivatives is the integration process. All right, so first, antiderivatives. So antiderivative functions, we usually label as capitals just to distinguish that we found an antiderivative, because it doesn't necessarily mean that my original function was a rate of change. I can actually find an antiderivative of any function, whether it's a derivative or not, whether it was originally a derivative or not. All right, so we usually do capitals. Right? Capital G would be any antiderivative. Usually it's the general case, right? The general antiderivative, that's why it's capital G, of some function. C is a constant, no number value. And so in order to be an antiderivative, alright, so in order for what we call the family of antiderivatives, or every antiderivative of my function, because there actually are infinitely many, we let the antiderivative be capital F of x. G is the general antiderivative. And then we have to tack on a constant. And I'll explain why in an example. Alright, suppose my original function, or not my original function, suppose the given function was 2x. Alright, so that's little f of x. My antiderivative, would be, what function gives me the derivative 2x? Alright, what function gives me this derivative? Because in order to be an antiderivative, the derivative of my antiderivative has to equal my original function. Right? That's what makes it an antiderivative. If that's true, it's an antiderivative of f of x. Well, what function has the derivative 2x? Well, the function that has the derivative of 2x is x squared. Right? That would be the general antiderivative. That would be the capital G of x. Alright, if I take the derivative of g of x, it equals 2x, and so the derivative of capital G of x is equal to the f of x, the little f of x. So don't know students get bogged down by the notation. Again, it's just a way to distinguish, because we have to have a way to distinguish, right? Prime means derivative, means rate of change function. And so when we do antiderivatives, we just use capitals. Again, it's just a way so when a reader reads something, we understand that's what we're talking about. All right, so this would be the general case, and then what we do is we tack on a constant. Because there are actually infinitely many functions that have this derivative, and the book talks about this in my lab videos, right? If I take the derivative of that does give me out 2x, which is equal to f of x. And what that plus c at the end does is it incorporates all possible answers, right? My original function could have been x squared plus 10. My original function could have been x squared minus 100. My original function could have been x squared minus square root of 2. Again, there are infinitely many examples of what the antiderivative could be, right? So if this is my function, all the possible antiderivatives, the family of antiderivatives, are anything with x squared plus some constant, right? And so there are infinitely many, right? Every single one of these that I've written down here, when I take their derivative, I get back to that 2x expression. Right? And so we have to tack on the constant c because that incorporates all possible answers. If we don't tack on the constant c, we just give the general case, which is one answer, but that might not be the answer we're looking for, and so you have to incorporate all the possible answers. All right, so that's what the antiderivative is. So integration is the process and the notation that mathematicians are about notation. Math is a language. All right, in the language we have notation, just like in any language, you have specific notation that has specific meaning. Well, the indefinite integral is the function, kind of like the plus symbol is the symbol that tells you to add two numbers together. The indefinite integral is the function that finds the family of all antiderivatives. Finds this family of all antiderivatives. All right, now it is, again, there is a reason behind the notation, and we don't get into it quite as much, because it's a sum notation. But it's the process of finding the antiderivative. The notation is this elongated sort of S symbol, and it's an elongated S symbol because it kind of comes from the sum. It's an infinite sum, and again, we don't get to go into the theory of that in this class. Alright, this would be the 2x. This would be the function I want to find the antiderivative of. The dx represents with respect to. This would be the differential. Alright? So this symbol right here is called the integrand. This is the differential. With respect to x. So again, it's a function where we have the differential, the derivative. You can think of it as terms of derivative. What we want to find is capital F of x, the family of antiderivatives. To do that, we find the general antiderivative, and then we have to tack on a constant. And so again, this would be the general antiderivative. And then this is just a constant. It represents all reals. Because in order for it to be the antiderivative, when I take the derivative, I should get that expression inside. Right? That's what makes it an antiderivative. Alright, so what's nice about integrals is there's fewer rules than derivatives that we go over. And you can always check your answer. This should always check. If I take the derivative of my antiderivative, it should get back to my original differential equation that's inside my integrand. Alright? And so now the rules. Alright, the basic rules. Now we will add to these rules at the end of chapter 4 2 more complex rules. But the basic rules, and again, I'm just going to kind of hit a basic. The My Lab video does a great job of explaining the family of antiderivatives, the integral, and all of that. So again, you make sure you watch those. They kind of talk about it in a little more detail. I didn't feel like re-going over the wheel. The reason why, again, you have to have that constant number C. So make sure you do look at those. All right, so the rules, again, I'm going to go over them again one more time, so I think it's always a good idea to hear them twice. And sometimes I talk about them a little differently than what the book does. Alright, so if I have a constant, so k is some real number value. So k is just a number. Remember, the d of x is with respect, so this is the derivative, the differential. Alright, what function gives me out the derivative, just a number? Well, that function that gives me out the derivative of just a number would have been just the x, right? So this would have been k times x plus some constant. An example of that would be something like, the antiderivative of 4/3 dt. Alright, so t is my variable. And so the antiderivative of that would be the 4/3 is the constant times t, which is the variable, and then plus some other constant here. C would be, again, if you take the derivative of, right, that would be my capital F of x, 4/3 t plus c. If I take the derivative of that, I do get my 4/3 back, right, my original expression. And so, again, if I have a constant inside, and that's all it is, the function rule is it's that constant times the variable part. The dt tells me what my variable part is. Alright, the second rule, the power rule. This is the one that's the most common. This is undoing the power rule. So remember, antiderivatives, working backwards from the derivative. This is the differential. This is the derivative. What function gave me that derivative? Well, I have to do the power rule in reverse. I'm going to undo the power rule. And so the first step is, remember, when we take the power rule, we multiply by the power and subtract 1. Well, we do the exact opposite in the exact opposite order here. We add 1 to the power, and instead of multiplying by that, we divide by that. And then again, there's some constant at the end. So if I've got an expression, x raised to the 1/2 dx. So again, that's my derivative, my differential. My power rule is I take my 1/2 plus 1, and I divide by that. Alright, and again, that's messy. That's, again, I'm just showing you the rule. But 1/2 plus 1 would give me 3/2. And then we divide by 3/2 and then tack on a c. Now, don't leave your answer like this. And again, actually, my rule of thumb is I usually write my expression instead of dividing by the fraction, remember we can multiply by the reciprocal. And so don't leave your answer as an improper fraction like this. Instead of dividing by the 3/2, multiply by the reciprocal 2/3. Alright, and there is my final answer. If I check this, if I take the derivative of this antiderivative, I do get back to my original expression, which is the 1/2. Right, I check to make sure it does. The reason why the 2/3 have to be out here, because when I take my derivative, I multiply by the 3/2. Well, I need the reciprocal of 3/2 in order for it to cancel out and give me out the 1 that's in front of my x term. And so if I do take the derivative of this, I do get those cancel out, so I do get x raised to the 1/2, and it does check. That is my antiderivative, my family of antiderivatives. And again, it has to have the plus c, because that's all possible antiderivatives. Constant times a function. So basically the constant can come out. The constant, again, it's the same rule as the derivative, right? When I have a constant out front, the constant comes along, I take the derivative of the function. Well, the same thing's true for the antiderivative. The constant just comes along, I take the antiderivative of the function part, and then I tack on a c. So if I have something like 1/3 x squared dx. Well, the 1/3 is going to come along, and I take the antiderivative of the x squared part. Well, the antiderivative of x squared would be x to the 3rd divided by 3, right? I add 1 to my power. That's where the 3 comes from. And then I divide by that because I'm undoing the power rule. And then don't forget there's that plus c at the end. And so my family of antiderivatives, I clean this up. I'm going to multiply this 3 times this 3 to get 1/9. X cubed plus c, right? There would be my antiderivative. If I took the derivative of that, I get back to my original expression. It does, right? I pull the 3 out. The 9/3 would reduce to 1/3, and it would be x to the 2nd, and then the constant would 0 out. Sum and difference rule works exactly like the derivative. I just look at each individual part. I take the antiderivative of f of x, add or subtract the antiderivative of g of x, and then tack on 1c. There's only 1c that you tack on. So this would be, again, where I've got more complex functions, something like 6x to the 3rd minus 2x plus the square root of 2 with respect to x. Alright, so I just look at each individual part. I look at the 6x cubed as an individual function, I look at the 2x as an individual function, and I look at the square root of 2 as an individual function. And so I use my rules. Well, the 6x cubed is the constant in the power rule, so is the 6 going to come along? I take the antiderivative of the power, so I add 1, I get 4, and then divide by 4. Now this one, you could probably do the antiderivative in your head, but I'm going to write out the rule. The 2 is going to come along. The antiderivative of x, remember x to the 1st would be, there'd be a 1 there. So I add 1 to get a square, and then I divide by that square. And then the square root of 2 is just a constant, so it'd be the square root of 2 times x, and then there's a plus c at the end. And then we clean it up, the family of antiderivatives, capital F of x. 6/4 will reduce down to 3/2 x to the 4th. The negative 2 will cancel out, give me a negative 1x squared, and then that's just the square root of 2 times x plus c. And there would be my family of antiderivatives. If I took the derivative of that expression, I would get back to this differential. Alright, rule 5 has to do with the e function, which again, there's 2 parts to it. There's the first one where it's just e to the x. Right, if I have the e to the x with respect to x, well, remember the derivative of e to the x is e to the x, which should make sense. The antiderivative is e to the x. Except you've got to add that constant to the end. It's e to the x plus c. So that would be the family of antiderivatives for the e to the x. That's the first part. Alright, the second part would be, well, what if I have something other than x? And for us, with antiderivatives, until we get to other rules, it'll just be a constant. So k is just a constant. K is a number. So like 2x, 0.1x, negative 1/3 x, or something like that. The rule is, well, it's e to the kx. So remember, if we would have taken the derivative of this, I would have multiplied by the derivative of k, or kx. I multiply by k. Well, we'll do the opposite. I divide by whatever that k is. So again, k is a number, and then don't forget the plus c. So I'm going to look at an example of the second case. Alright, suppose I have e to the x where I've got 10e to the 2x. Push back to x, right? Well, the 10 is going to just come along when I take the antiderivative. The derivative of e to the 2x, well, is this rule. It's e to the 2x, but I'm not done yet. I have to divide by that 2 out front, because if I had taken a derivative, I would have multiplied by 2. So the antiderivative is the exact opposite. I divide by the 2. So it's e to the 2x, divide by 2, and then don't forget there's the plus c at the end. Simplify that. Well, 10 divided by 2 is going to give me 5e to the 2x. And whenever you're unsure, take the derivative of this. If I take the derivative of my final answer, I would get 5e to the 2x times 2, right? Because it's the derivative of e is itself times the derivative of the 2x, which is 2, and that simplifies the 10e to the 2x. And so it checks. I get back to my differential part. Alright, the last rule for right now, until we get to the later sections, would be the function if I've got x raised to the negative 1. If you try to use your power rule here, what happens is, well, if I try to use my power rule, right, the power rule is I add 1 and then divide by that. Well, what happens when I take negative 1 plus 1? Well, that gives me a division by 0, and that doesn't work. Because this is a special case, right? X to the negative 1 really is the function 1 over x. Remember, this is the differential. This is the derivative. What function gives me the derivative 1 over x? Well, remember, that's our natural log function, right? Our ln of x plus c. Now, note, it just says x is not 0, and so remember, this original function actually has, so there's an additional part to this. This is only true if x is greater than 0. Alright, so the way we get around the if x is greater than 0, instead of just writing that out, what we do instead, well, we know we want x to be positive, and so what we write, in order to guarantee that we have positive values that go into my natural log, well, we write the absolute value. Right, so that guarantees it's going to work for all x values of my original function. Right. Again, x is not 0, still can't be 0. Can't plug 0 into the natural log. But I can't plug 0 into this original function here either. Could plug negative values into that. Can't plug negative values into my natural log. And so to get around the if x is greater than 0, we put the, so you always have to put absolute values of this. Right, so if you've got the natural log rule, 1 over x, you always have to take absolute value of it. Alright, so again, just remember that. It's something you have to remember. It's sort of an extra step that you have to remember. Alright, so there's the rules. We'll get into practicing these in the next videos.